All right. Good morning, everybody. Today is Wednesday, December 27th, 2017. And this is Before the First Cup with Jules here on UCY.TV. Happy Wednesday, everyone. Hope you had a good holiday. So with the holidays, it is always kind of hectic for me, so I had to take a couple days off. But we listened to a couple good lectures that we're going to talk about today. We're going to continue on looking a little bit at nanotechnology and some of the things that is happening with it right now and where it is being used in the industry. So where did we leave off yesterday? We titled the show Robert Freitas, Nanofactories and Healthcare Nanobots. And that was an encore back from 2015, I believe. It was an interview run by Ray Kurzweil interviewing Robert Freitas in regards to nanofactories and building upon some ideas from Eric Drexler, who we actually heard on Monday, and healthcare nanobots, something that is very near and dear to Kurzweil's heart. So let's take a look. Who is Robert Freitas? His career, he holds a bachelor's degree in physics and psychology back from 1974, and he got his law degree, his Juris Doctor, back in 1978. He's written more than 150 technical papers, book chapters, and popular articles on a diverse set of scientific, engineering, and legal topics. Freitas began writing his nanomedicine book series in 1994, published in 1999, while Freitas was a research fellow at the Institute for Molecular Manufacturing. In 2003, he was part of the bioscience group. In 2004, Freitas and Ralph Merkel co-authored and published Kinematic Self-Replicating Machines, which is a comprehensive survey of the field of physical and hypothetical self-replicating machines. Now, Ralph Merkel, I never heard of him before this morning, but I came across him connected to not only Ray Kurzweil and Eric Drexler, but also to Robert Freitas. Ralph Merkel was actually one of the inventors of cryptography. Yes, he is one of the inventors of public key cryptography, the inventor of cryptographic hashing, and more recently a researcher and a speaker on cryonics, and they'll be freezing the body to bring him back again after death. He has worked on all kinds of things, as well as been a part of Xerox, and he was also a nanotechnology theorist for a company named Zyvex. What I think is neat is that one of his inventions in cryptography is being used. It's called the Merkle tree. His name is Ralph Merkel, and it is being used in blockchain. So the fact that we have this individual who was the inventor of cryptography working together with the nanotechnology people, to me, is a little bit frightening. I don't know what the implications of that is, but it is a little bit interesting to see how cryptographic technologies are spreading across the internet. And we have Singularity Net with Ben Goertzel, who are using their Singularity Net blockchain to help fund and fuel the creation and the proliferation of artificial intelligence. Freitas, so he worked with Merkel, and they published a survey of physical and hypothetical self-replicating machines. 2009, Freitas was awarded the Feynman Prize in nanotechnology. It seems there's a bunch of people who have won that prize. And he also created the sentience quotient, which was a concept in 1977 to 78 as a way to describe the information processing rate in living organisms or computers. Now, why is that important? Well, the information processing rate in living organisms or computers, what they've been trying to crack for a very long time. Our biological bodies are very sophisticated computers, they've discovered, and they're able now to mimic biology. And as they get better and better with their spectroscopy and their high-resolution microscopes, they are able to view biological processes happening in real time that then they can mimic in the laboratory. On Monday, we titled the show Eric Drexler, Nanotechnology, Remaking the 21st Century. And this was all about molecular manufacturing and how we can reverse engineer. Instead of starting on the big end in a large factory, we could do desktop engineering. Wikipedia on Eric Drexler. His full name is K. Eric Drexler. He was born in 1955. He's an American engineer, most known for popularizing the potential of molecular nanotechnology from the 1970s and the 1980s. His 1991 doctoral thesis at MIT was revised and published in a book called Nanosystems, Molecular Machinery, Manufacturing, and Computation in 1992, and he received the Association of American Publishers Award for Best Computer Science Book of 1992. He was strongly influenced by ideas on limits to growth in the early 1970s, and during his first year at MIT, he sought out someone who was working on extraterrestrial resources. He founded the Gerald K. O'Neill of Princeton University, a famous physicist for his work on storage rings and particle accelerators, and his landmark work on the concept of space colonization. So this is who Drexler sought out. Drexler then participated in a NASA summer studies on space colonies in 75 and 76. And he fabricated metal films a few tens of nanometers thick and a wax support to demonstrate the potentials of high-performance solar sails. Now, you know who's working on the solar sails project? That would be Stephen Hawking, and there was some other tech billionaire that was involved to send those little nano satellites. I don't remember what they were called. They were 1 centimeter by 1 centimeter by 1 centimeter to Alpha Centauri. Drexler was also active in space politics, and he helped the L5 Society defeat the Moon Treaty in 1980. And besides working summers for O'Neill, building mass driver prototypes, Drexler delivered papers at the first 3 space manufacturing conferences at Princeton. In 77 and 79, papers were co-authored with Keith Henson, and patents were issued on both subjects, vapor phase fabrication and space radiators. During the late 1970s, Drexler helped develop ideas about molecular nanotechnology, and in 79 he encountered Richard Feynman's provocative 1959 talk, There's Plenty of Room at the Bottom. In 81, Drexler wrote a seminal research article published called Molecular Engineering, a Approach to the Development of General Capabilities of Molecular Manipulation, and the article continues to be cited more than 620 times during its following 35 years. The term nanotechnology has been coined by the Tokyo Science University professor Norio Taniguchi in 1974, and I have one of his papers pulled up here to describe the precision manufacture of materials with nanometer tolerances, and Drexler unknowingly used a related term in his 1986 book, Engines of Creation, to describe what later is known now as molecular nanotechnology. Remember, Freitas took molecular nanotechnology a step further and applied it to medical practices. In Engines of Creation, Drexler proposed the idea of nanoscale assemblers, which would be able to build a copy of itself of other items of arbitrary complexity. He also first published the term gray goo, which he was sorry he did, to describe what might happen if a hypothetical self-replicating molecular nanotechnology went out of control. Oh no! And he subsequently tried to clarify his concerns about the out-of-control self-replicators and make the case that molecular manufacturing does not require such devices. Now, Freitas and Kurzweil actually talked about gray goo in the interview we heard yesterday, and I thought it was interesting that Freitas' solution was to use some sort of satellite scanning that can look at heat signatures and be able to tell where the nanotechnology was going out of control. I don't know about that. I think it sounds like a little bit of a pipe dream that they would think they would be able to see it on satellite, but maybe. In March of 2004, Drexler signed scientists in an open letter to support cryonics. So he's another one that is involved with freezing yourself after death to bring you back. In August 2005, Drexler joined Nanorex, which is a molecular engineering software company based in Bloomfield Hills, Michigan, to serve as the company's chief technical advisor Nanorex's Nano Engineer -1, and its software was reportedly able to simulate a hypothetical differential gear designed in a snap. Well, good. So what does that mean? Well, back on Friday, we had looked at DARPA, self-assembling programmable matter, Drexler, and gray goo. So let's take a look a little bit at what gray goo is, because this is where we should be worried. We have artificial intelligence that has already been let out of the bottle onto the internet, place where once it got, you're not going to be able to stuff it back into that bottle. Now we have nanotechnology that is running amok. There's an entire national nanotechnology initiative that is going on right now that I didn't know about until today either. We're going to look at that. But let's look at this. So gray goo is a hypothetical end-of-the-world scenario involving molecular nanotechnology in which out-of-control, self-replicating robots consume all the biomass on Earth while building more of themselves. A scenario that has been called ecophagy, and the idea assumes that machines were designed to have this capability, while popularizations have assumed the machines might somehow gain this capability by accident or accidentally on purpose. Self-replicating machines of the macroscopic variety were originally described by mathematician John von Neumann and are sometimes referred to as the von Neumann machines or clanking replicators. The term gray goo was coined by nanotechnology pioneer Eric Drexler in his 1986 book, Engines of Creation. And in 2004, he stated, "I wish I had never used the term gray goo." Whoops. Because people said, wait a minute, is there even a possibility of this, that you're going to create these micro machines that could potentially consume all of the biological material on Earth to fuel themselves? Well, maybe, just maybe. Engines of Creation mentioned gray goo in 2 paragraphs and a note. While popularizing the idea of gray goo was first publicized in a mass-circulated magazine called Omni, and we read about that, and it got people scared. So where do we go from here? Is Programmable Matter actually coming soon? May 1st, 2016 by Tim Youngblood. There are all kinds of speculations and supposed breakthroughs in the field of programmable matter, but how close are we really? Whether it is the T-1000 from Terminator, the Autobots, the Decepticons, or that awesome 3D pinboard from X-Men, we read this on Friday, I think, you've probably seen some version of programmable matter in the movies. The term programmable matter was coined in 1991, and we've been fascinated by the concept ever since. The eventual goal is to have microscopic machines that can rearrange their grouping, allowing them to take any form of our choosing, and maybe even get inside your body to fix and repair you. Back in 2010, the famed physicist Michio Kaku spoke about the technology's potential in an interview with Big Think, and I actually found that interview, and it should be in my RSS feed for Twitter. It'll be a long time before we have anything that cool, but the field of self-reconfiguring modular robotics has produced some intriguing devices that could potentially be the precursor to our science fiction fantasies come to fruition, or nightmares. The modular robotics breakthrough that we do have today are shape-shifting tables, 4D printed robots that can fold into different shapes, and cubes that can rearrange themselves using magnetism. If any of these technologies can be scaled down successfully, we might get to see the microscopic programmable matter in our lifetime. Well, guess what? Hold on one second. Let's get this page to load. So this is September 14th, 2017. And this, I would say, was close enough. We have nanorobots made out of DNA. This is published out of caltech.edu. Sorting molecules with DNA robots. A DNA nanobot is programmed to pick up and sort molecules into predefined regions. There'll be molecules in the outside world or in the inside world inside of your body. Imagine a robot that could help tidy up your home, roving about, sorting stray socks into laundry and dirty dishes into the dishwasher. While such a practical helper may be the stuff of science fiction, Caltech scientists have developed an autonomous molecular machine that can perform similar tasks at the nanoscale. So it happened, people. And this robot is made of a single strand of DNA and can autonomously walk around on a surface, picking up certain molecules and then dropping them off in designated locations. The work was done in the laboratory of Lulu Kwang, an assistant professor of bioengineering, and it appears in the paper of September 15th issue of Science. So why nanobots? Well, just like electromechanical robots that are sent off to faraway places like Mars, we would like to send molecular robots to minuscule places where humans can't go, such as in your bloodstream, says Kwan. Our goal was to design and build a molecular robot that could perform a sophisticated nanomechanical task of cargo sorting. So led by a former graduate student, Inupa Thalgubri, who got their PhD in 2017, the researchers constructed 3 basic building blocks that could be used to assemble a DNA robot, and that was a leg with 2 quote-unquote feet for walking, an arm and a hand for picking up cargo, and a segment that can be recognized as a specific drop-off point and a signal to the hand to release its cargo. Each one of these components is made up of just a few nucleotides with a single strand of DNA. In principle, these modular building blocks could be assembled in many different ways to complete different tasks. It would be a DNA robot with several hands and arms, for example, could be used to carry multiple molecules simultaneously, so speeding up the progress. Hold on one second. In the work described in the science paper, Kwan's group built a robot that could explore a molecular surface and pick up 2 different molecules. One was a fluorescent yellow dye and one was a fluorescent pink dye, and then distribute them to 2 distinct regions on the surface. Using fluorescent molecules enabled the researchers to see if the molecules ended up in their intended locations. The robot successfully sorted 6 scattered molecules, 3 pink, 3 yellow, into their correct places in just 24 hours, and adding more robots to the surface shortened the time and it took to complete the task. Now, I thought Freitas had talked about billions of these little things inside of our bloodstream. And though we demonstrate a robot for this specific task, the same system can be designed to do generalized work with just a dozen different types of cargo at any arbitrary initial location on the surface. One could have multiple robots performing diverse sorting tasks all in parallel. Remember, parallel computing is how they get supercomputing. The key to designing DNA machines is the fact that DNA is a unique chemical and physical property that's known and it is programmable. A single strand of DNA is made up of 4 different molecules called nucleotides, and that would be the C, A, T, and G, and arranged in a string called a sequence. These nucleotides bond in specific pairs, A with T, C with G, and remember, we also have X and Y, which are your synthetic nucleotides in synthetic biology. And when a single strand encounters a so-called reverse complementary strand, that would be CGATT and AATCG, 2 strands zip together in a classic double helix shape. Well, that sounds a lot like CRISPR, but synthetic CRISPR. The single strand containing the right nucleotides can force 2 partially zipped strands to unzip from each other. How quickly each zipping and unzipping event happens and how much energy it consumes can be estimated for any given DNA sequence, allowing researchers to control how fast the robot moves and how much energy it uses to perform the zipping and unzipping tasks. So these robots are going to go in and genetically modify living material, is what this sounds like to me. Additionally, the length of a single strand or 2 zip strands can be calculated, and thus the leg and the foot of the DNA robot can be designed for a desired step size, in this case 6 nanometers, which is about 100 millionth of a human step size. Using these chemicals and physical principles, researchers can design not only robots, but also playgrounds, robot playgrounds inside of you, such as molecular pegboards to test them on. And in the current work, the DNA robot moves around on a 58 nanometer by 58 nanometer pegboard, in which the pegs are made of single strands of DNA complementary to the robot's leg and foot. The robot binds to a peg with its leg and one of its feet, and the other foot floats freely, and when the random molecular fluctuations causes free foot to encounter a nearby peg, it pulls the robot to the newest peg, and its other foot is freed. The process continues with the robot moving along in a random direction at each step till it gets to the desired location. It may take a day for the robot to explore the entire board, and along the way, as the robot encounters cargo molecules tethered to the pegs, it grabs them with its hand components and carries them around until it detects the signal to drop them off. The process is slow, but allows for a very simple robot design that utilizes very little chemical energy. So now, what are the futuristic applications of this type of horror? Molecular robots that they can put inside of our bloodstreams. Well, we don't develop DNA robots for any specific applications, so don't worry about it, wink. Our lab focuses on discovering the engineering principles that enable the development of general-purpose DNA robots. However, it is my hope that other researchers could use these principles for exciting applications, such as using DNA robots for synthesizing a therapeutic chemical form and its constituent parts into an artificial molecular factory. Oh no, delivering a drug only when a specific signal is given in the bloodstream or within the cells, or by sorting molecular components into the trash for recycling. The paper is titled A Cargo Sorting DNA Robot, and in addition to Thingabear and Kwan, other co-authors of the postdoctoral scholar Wei Li, graduate student, blah, 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 blah. All right. So to continue on the story, so that was from September of 2017. Now out of Eureka Alert, December 14th, 2017. Single-stranded DNA and RNA origami go live. Oh, remember when they were working on the origami robo-bees and the self-assembling robots as part of the Weiss Institute? Well, now we have it with DNA and RNA. And remember, Georgie Church is involved over at Harvard as well. The first nanotechnological approach enables the design and replication of complex single-stranded DNA and RNA origami with a potential for drug delivery and nanofabrication. The Weiss Institute for Biologically Inspired Engineering at Harvard. Ding, ding. Nanotechnologists are using DNA, the genetic material present in living organisms, as well as its multifunctional cousin RNA, as the raw materials in efforts to build minuscule devices that could potentially function as drug delivery vehicles, tiny nanofactories for the production of pharmaceuticals and chemicals, and highly sensitive elements of electric and optical properties. Like genetic DNA and RNA in nature, these engineered nanotechnological devices are also made up of strands that are comprised of the 4 bases known as CATG regions, so those strands can spontaneously fold and bind to each other via short complementary base sequences in which A's from one sequence specifically bind to T's from another sequence, and C's bind to G's as well. Researchers at the Weiss Institute of Biologically Inspired Engineering and elsewhere have used these features to design self-assembling nanostructures such as scaffolded DNA origami and DNA bricks with ever-growing sizes and complexities that are becoming useful for diverse applications. Yeah, these are self-assembling, guys. Let's hope they don't turn into nano gray goo made out of DNA. However, the translations of these structures in medical and industrial applications is still challenging, partly because these multi-stranded systems are prone to local defects due to missing strands. In addition, they self-assemble from hundreds to thousands of individual DNA sequences that need to be verified and tested for high-precision applications, and whose expensive synthesis often produces undesired side products. Yeah, just like off-target cutting with CRISPR. So now a novel approach published by Science and a collaborative team of researchers from Weiss Institute, Arizona State University, as well as the makers of AutoCAD called Autodesk, who were working on a synthetic biology project, if I remember correctly, for the very first time enabled the design of a complex single-stranded DNA and RNA origami that can autonomously fold into diverse, stable, user-defined structures. And in contrast to the synthesis of multi-stranded nanostructures, these entirely new types of origami are folded from one single strand, which can be replicated in living cells, allowing the potential low-cost production at very large scales and with high purities, opening entirely new opportunities for diverse applications such as drug delivery and nanofabrication within the human body. Earlier generations of larger-sized origami are composed of central scaffolding strands whose folding and stability requires more than 200 short staple strands that bridge distant parts of the scaffold and fix them in space. In contrast to traditional scaffolding origamis, which are assembled from hundreds of components, our new approach allows us to reliably design and synthesize stable, single-stranded, and self-folding origami, says Weiss Institute core faculty member and corresponding author Peng Yin, PhD. Our fundamentally new approach relies on single-strand folding rather than multi-component assembly to produce large nanostructures, and this, together with the ability to basically clone and multiply a single component strand in bacteria, presents a game-changing advance in DNA nanotechnology that greatly enhances single-stranded origami's potential for real-world application. Yin is also co-lead of the Weiss Institute's Molecular Robotics Initiative and professor of systems biology at Harvard Medical School. Yeah. All right, this is the guy that we want building self-replicating DNA and RNA nanobots to first enable the production of single-stranded and stable DNA-based origami with distinct folding patterns. The team had to overcome several challenges in a large DNA strand that goes through a complex folding process. Many sequences need to accurately pair up with sequences that are far away from each other. And if this process does not happen in an orderly fashion, then the strands get tangled and form unspecific knots along the way, rendering it useless. To avoid this problem, which you don't want to happen inside of you, to avoid this problem, we identified new design rules that we can use to cross DNA strands between different double-stranded regions and develop a web-based automation design tool that allows researchers to integrate many of these events into a folding path, leading to a large, knot-free nano complex. So it sounds to me like they're building little nano networks. The largest DNA origami structure created previously was assembled by synthesizing all their constituent sequences individually in vitro and then mixing them together. And as a key feature of the new design process, the single-strandedness of the DNA origami allows researchers to introduce DNA sequences stably into E. coli and inexpensively and accurately replicate these with every single cell division. Oh my God. If this could greatly facilitate the development of single-stranded origami for high-precision nanotech like drug delivery vehicles, for example, as not only a single easy-to-produce molecule needs to be validated and approved. Finally, the team also adapted single-stranded origami technology to RNA, which has a different nucleic acid material, and it offers certain advantages, including, for example, even higher production levels in bacteria and usefulness for potential intracellular and therapeutic RNA applications. Oh, get excited. Translating the approach to RNA also scales up the size and complexity of synthetic RNA structures, and tenfold compared to previous structures made from RNA. Hey, just as a side note here, I don't know if I mentioned at the beginning of the show that it was 7 degrees here with a real feel of minus 11. It is pretty damn cold here, and I'm under a blanket, and I'm still freezing even with the heat on. Their proof of concept analysis was also proved to be protruding DNA loops that can be precisely positioned and used as handles for the attachment of functional proteins. And in the future development, single-stranded origami could thus be potentially functionalized by attaching enzymes, fluorescent probes, metal particles, or other drugs either to the surfaces or within the cavities inside. And they could effectively convert single-stranded origami into nanofactories, light sensing and emitting optical devices, or drug delivery vehicles. So we could maybe even make DNA-level optogenetics tools for inside the body. And this is just nuts. This new advance by the Weiss Institute's Molecular Robotics Initiative transforms an exciting laboratory research methodology into a potentially transformative technology that can be manufactured at large scales by leveraging the biological machinery of living cells. Oh, how great this is. And to work, it opens a path by which DNA nanotechnology and origami approaches may be translated into products that meet real-world challenges. says Weiss Institute founding director Donald Ingeber, who is also the Judah Folkman Professor of Vascular Biology and the Vascular Biology program of Boston Children's Hospital, as well as Professor of Bioengineering at Harvard. And he's a smart cookie. The results announced today, December 14th, 2017, established DNA nanotechnology as a viable alternative approach for applications that have the potential to benefit all of us as a nation, says Jim Krause, assistant professor of the National Science Foundation's Directorate for Computer and Information Science and Engineering. We are delighted this work was supported by the National Science Foundation's expeditions in computing programming, which has over the last decade funded large teams of researchers to pursue ambitious, fundamental research agendas that help define and shape the future of computer and information science and engineering and impact our national competitiveness. Now notice this is under computer engineering, except this is biological engineering. Whoops. How did that happen? Well, we're going to back up just a little bit here. This is a paper out of MIT Lab for Computer Science from 1987, and this is written by Norman Margolis and Tommaso Toffoli, who's mentioned in some of this earlier stuff that we had read about. This paper is from 1987, Complex Systems, Cellular Automata Machines. The advantages of an architecture optimized for cellular automata simulations are so great that for large-scale cellular automata experiments, it becomes absurd to use any other kind of computer. The focus of the research conducted by the Information Mechanics Group at MIT Laboratory for Computer Science has been the study of the physical basis of computation and the computational modeling of the physics-like systems. Much of the research has been involved in reversible models of computation and cellular automata. In 1981, the frustrating efficiency of conventional computing architectures for simulating and displaying cellular automata became a serious obstacle to our experimental studies of reversible cellular automata. Even using conventional components, it was clear that several orders of magnitude and performance could be gained by devising hardware which would take advantage of the predictability and the locality of the updating process. And the first prototype was a sequential machine which scanned a two-dimensional array of cells, producing new states for the cells fast enough and in the right order so they could keep up with the beam of an ordinary raster scan television monitor. And after a few years of experimentation and refinement, arrangements were made for a version of our machine, namely the CAM6, to be produced commercially so that it would be available to the general research community. Isn't that nice? Commercial production. So what is cellular automata? This is a quote out of Scientific American 1970. To play life, and that is kind of what they are doing here, you must have a fairly large checkerboard and a plentiful supply of flat counters of two colors. And it is possible to work with a pencil and graph paper, but it is much easier, particularly for beginners, to use counters and a board. Now, isn't that how they were just talking about doing that DNA nanotechnology was with a little pegboard? In this chapter, we are going to get away from talking about vectors in motion, and this is nature of code. In fact, the rest of this is going to focus mainly on systems and algorithms, albeit ones that we can and we should apply to moving bodies. We encountered our first processing example of complex systems, and that would be flocking. And then we talked about core principles behind complex systems. Complex systems are more than a sum of their parts. A complex system is a system of elements that operate in parallel and in short-range relationships that as a whole exhibit emergent behavior. This is going to be dedicated to building another complex system, and that would be a simulation and processing. Oddly, we're going to take a step backward and simplify the elements of our system. No longer are the individual elements going to be members of the physical world. Instead, we will build a system out of the simplest digital elements possible, and there'll be a single digit or a bit. And this bit is going to be called a cell, and its value is going to be either a 0 or a 1, and it will be called the slate. Working with such simple elements will help us understand more of the details behind how they work, complex systems work. We'll be able to elaborate on some programming techniques that we can apply to code-based projects. For one, let's get this thing straight. The term cellular automata is plural. Our code examples will simulate just one, and that would be a cellular automation. And to simplify our lives, we'll also refer to cellular automata as CA. We looked at objects, which are movers, particles, vehicles, and voids generally existing in only one state. And they might have moved around with advanced behaviors in physics, but ultimately they remain the same throughout the course of their digital lifetime. Cellular automaton is a model of systems of cell objects with the following characteristics. These cells live on a grid. Each cell has a state, and each cell has a neighborhood. The development of cellular automata systems is typically attributed to Stanislaw Ulam and John von Neumann, who were both researchers at the Los Alamos National Laboratory in New Mexico back in the 1940s. Ulam was studying the growth of crystals, and von Neumann was imagining a world of self-replicating robots. That's right, robots that could build copies of themselves. And once we see some examples of cellular automata visualized, it might be clear how one might imagine modeling crystal growth, and the idea of robots then follows along. Consider the designing of a robot as a pattern on a grid of cells, and now consider a set of simple rules that would allow for the pattern to create copies of itself on that grid. This is essentially the process of cellular automata that exhibits behavior similar to biological reproduction and evolution. Ding, 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 ding. So they have reduced technology down to zeros and ones, and then they've drawn parallels to how this works in biological organisms. Von Neumann's work in self-replication and cellular automata is conceptually similar to what is probably the most famous cellular automaton, and that would be the game of life, which we will discuss in detail later in this section. Perhaps the most significant scientific and lengthy work studying cellular automata arrived in 2002 with Stephen Wolfram's 1,280-page book called A New Kind of Science. Available in its entirety free online, and a link to this. Wolfram's book discusses how cellular automata is not simply neat tricks, but it is relevant to the study of biology, chemistry, physics, and all branches of science. This chapter will barely scratch the surface of the theories of Wolfram, but its examples provide enough sparks for your curiosity, and you will find plenty of more to read about in his book. The examples in this chapter will begin with a simulation of Wolfram's work. To understand Wolfram's elementary cellular automata, we should ask ourselves the question, what is the simplest cellular automaton we can imagine? What is exciting about this question and its answer is that even the simplest cellular automaton imaginable will have properties of complex systems at work. So I don't know how much in detail we want to get this. All right, so what is the peril of programmable matter? Because that is what we are talking about. One popularized doomsday prediction for the technology like programmable matter is called the gray goose scenario, which is a hypothetical outcome where nanoscale robots consume all of Earth's biomass in order to either self-replicate or construct some pre-programmed product or biological organism. While some far-out sci-fi scenarios pose an actual risk, like runaway artificial intelligence, it seems that gray goose scenarios are really just that of science fiction. Yeah, when was the date of this? Hold on. Let's scroll up. Beep, 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 beep. This was May 24th, 2017. Well, yeah, this was before they were doing self-replicating RNA and DNA robots. All right, this was the promise. Now let's go down to the peril. Policy investigation into the effects of advanced nanotechnology should consider this as a primary concern, and a runaway replication is a more distant issue, so don't worry about it. If a soldier in battle can reach into a paint can and pull out a hammer, why couldn't they pull out something much more devastating? Why couldn't a civilian with access to similar technology craft powerful weapons unbeknownst to any authority? As Phoenix co-author Eric Drexler points out, there are many concerns like these that have to be addressed as programmable matter technology advances. An obsession with obsolete science fiction images of swarms of replicating nanobugs has diverted the attention from real issues raised by the coming revolution in molecular nanotechnology, says Drexler. Yeah, shh. Don't worry about what could happen. We need to focus on the issues that matter, and that is how to make these powerful new capabilities in a competitive world. Of course it is. So what exactly will we obtain these powerful capabilities of programmable matter? Well, as we have seen, research into the subject is both active, varied, and fruitful, and despite some overly optimistic expectations, unless DARPA is holding out on us, it seems inevitable that our engineering capabilities will eventually catch up with our futuristic fantasies. Of course, whether that offers an end to scarcity or leaves us all as gray goo remains to be seen. Right. So what are your programmable matter predictions? Yes, I say we're all going to turn into gray goo. So then I ran across this morning, the National Nanotechnology Initiative. So what is that, you ask? The National Nanotechnology Initiative is a United States federal government program for the science, engineering, and technology research and development for nanoscale projects. The NNI, and that would be the National Nanosecurity Initiative, serves as the central point of communication, cooperation, and collaboration for all federal agencies engaged in nanotechnology research, bringing together an expertise needed to advance this broad and complex field. Initiative participants cited below state that the four goals are: 1, to advance a world-class nanotechnology research and development program. 2, foster the transfer of these new technologies into products for commercial and public benefit, yes, like your healthcare. 3, develop and sustain educational resources, a skilled workforce, and supporting infrastructure and tools to advance nanotechnology. And 4, support responsible development of nanotechnology as well. So who is funding this and who has the budget? Well, number 1 is the National Institute of Health. So that should put the writing on the wall. 2 is the National Science Foundation. 3 is the Department of Energy. 4 is the Department of Defense. 5 is the National Institute of Standards and Technology, more affectionately known as NIST. 5 is the Department of Homeland Security. 6 is the United States Department of Agriculture. 7 is NASA. 8 is the Food and Drug Administration, and 9 is the EPA, and 10 is other. Wink. We don't know who other is. So what's the history? Well, back in 1999, there was an initiative proposed to the White House of the Clinton administration. Bill Clinton advocated nanotechnology development in a January 21st, 2000 speech at the California Institute of Technology. And Clinton stated that some of our research goals may take 20 or more years to achieve, but that is precisely why there is an important role for the federal government. George W. Bush further increased funding for nanotechnology. December 3rd, 2003, Bush signed into law the 21st Century Nanotechnology Research and Development Act, which authorized expenditure for 5 of the participating agencies totaling $3.63 billion over 4 years. This law is an authorization, not an appropriation, and its subsequent appropriations for these 5 agencies that have not met the set out goals for 2003. However, there are many agencies involved in the initiative that are not covered by this act and requested budgets under the initiative for all participating agencies in the fiscal year of 2016 to 2006 to 2015 totaled over $1 billion each. In February of 2014, the National Nanotechnology Initiative released a strategic plan outlining updated goals and program area components as required under the terms of the Act. The document supersedes any previous documents released. The National Nanotechnology Institute's budget supplemented proposed by Obama for fiscal year 2015 provided $1.5 billion in requested funding, and the cumulative investment since 2001, which includes the 2015 requests, totals almost $21 billion spent on developing nanotechnology. So this is your tax dollars at work. Cumulative investments in nanotech-related environmental, health, and safety research since 2005 now totals nearly $900 million, and federal agencies with the largest investments are the National Institute of Health, National Science Foundation, Department of Energy, Department of Defense, and the National Institute of Standards and Technology. So now, let's take a look at their website. It is nano.gov. Who would have thunk it? Nano.gov, the National Nanotechnology Initiative. Scientists shape DNA into donuts, teddy bears, and an image of the Mona Lisa. So again, your tax dollars being spent well. Scientists have made big advances in the building of shapes out of these so-called building blocks of life. I couldn't even believe this. They made DNA donuts and teddy bears and a Mona Lisa. Scientists have made a big advance in building shapes out of the so-called building blocks of life. New techniques can shape DNA, which is the double-stranded helical molecule of encoded genes, into objects up to 20 times bigger than previously achieved. This was December 6, 2017. 3 separate groups reported today. Together with these new approaches, they can make objects into virtually any shape. 3D donuts and dodecahedron cubes, as well as teddy bears and shaped cutouts, even a tiled image of the Mona Lisa. And the techniques could someday lead to a bevy of novel devices for electronics, photonics, nanoscale machines, and possibly even for disease detection. Scientists have been making shapes out of DNA since the 1980s, and those efforts took off in 2006 with the invention of a folding technique called DNA origami. Oh, we come full circle. It starts with long DNA strands called scaffolds that have precise sequences of 4 molecular units or nucleotides dubbed C, A, T, and G, in which DNA spells out its genetic code. Researchers match patches of the scaffolding to complementary strands of DNA called staples, which latch onto their targets in 2 separate places, and connecting those patches force the scaffold to fold into a prescribed shape. A second version of the technology, introduced in 2012, only uses small strands of DNA, but no scaffolds, that lets the assembly into Lego-like bricks that can then all be linked together. Both approaches have been wildly popular among nanotechnologists, allowing them to design shapes made from DNA from the bottom up. This is like Eric Drexler's wet dream. Researchers have also been able to coat their DNA objects with plastic, metals, and other materials to fashion tiny machine components, electronics, and photonic devices, but the size of the conventional DNA objects has been limited to about 100 nanometers. If you grew them any larger, they become too floppy to make a particular shape and cannot make enough connections to their neighbors to get bigger. I think that was part of like that cellular automata. Well, not anymore. Groups in Germany, Massachusetts, and California all reported today in Nature magazine that they have made DNA objects with newfound heft. The German team, led by Hendrik Dietz, a biophysicist at the Technical University of Munich, modified the traditional origami approach, using it to create rigid DNA molecules with pre-programmed shapes that can assemble with other copies to build specific shapes. For example, in solution, DNA strands designed to fold up into 3D wedges combined with other to form a miniature donut about 300 nanometers across, and modules that form 3-pronged vesicles, assemble into various objects, including dodecahedrons that are 440 nanometers wide. The Massachusetts team, led by Pin Ying, and that would be from the Weiss Institute, and he is a system biologist at Harvard's Weiss Institute of Biologically Inspired Engineering, modified the DNA brick approach, which they invented to make larger, more complex structures. In the original technique, each Lego-like brick has a DNA linker, which was 8 nucleotides long, that locks it in place with its neighbors. This new approach uses links of 13 nucleotides each. And in their paper, Yin and his colleagues explained how to create a block composed of 33,000 bricks and 1.7 million DNA nucleotides. By leaving out bricks in the center of such blocks, they also created cutouts shaped like everything from an hourglass to a teddy bear. And though such void structures aren't yet useful, the technique gives us the ability to engineer highly complex living systems. Now, we had read about them building living supercomputers. Now, I want to fast forward here a little bit, because this was a story that I ran across last Friday. Programmable matter in medical technology, the origami robot made of meat. Yes, of meat. Researchers from the U.S.'s MIT and Japan's Tokyo Institute of Technology and UK's Sheffield University have all developed new medical robots made from programmable matter and pig intestines. MIT's CSAIL, and that is the Computer Science and Artificial Intelligence Laboratory, has released the announcement of a tiny ingestible robot designed to be swallowed and sent to perform tasks within the human body. The robot is the newest in a series of programmable matter robots known as origami robots, so named because of their ability to fold themselves into different shapes. These programmable matter robots are able to change shape based on pre-installed creases in the semi-rigid material they're constructed out of. And by inputting different algorithmic electrical signals, the robot's shape memory allies are able to assemble themselves into different shapes without being physically touched. The robots activate and unfurl when they are exposed to heat, and then they are controlled via external programmable actuation. In other words, the robots are controlled and they are programmed by magnetic fields generated externally. This is made possible by a small magnet folded into the programmable material. Now, I want to see if I can scroll up here quickly before the end of the show, because there was another story. Oops, slow down there, Chappie. There was another story getting into programmable nano. If I can even click on this one. Oh, hurry up, damn it. Hurry up. I'm reaching the limits. Hurry up. This was in Lithuania. Hold on one second. All right, December 27th, so that was today at 2 a.m., 2017, out of Lithuania, Nano Jesus 10,000. Lithuanian scientists have reduced a life-size nativity scene 10,000 times to create a Christmas present for the Pope that is smaller in size than the size of a cell and invisible to the naked eye. Besides an attempt to impress the Pope before he visits the country next year, the Lithuanian government is using the mini model to promote the country as a hub for cutting-edge technology. So that's Nano Jesus 10,000. And remember, they are working all over the globe with these types of technology, even creating little nanorobots out of pig intestines. So, Massachusetts Institute of Technology has created 33,000 bricks and 1.7 million DNA nucleotides that create a chunk of blocks. And then they were able to make shapes inside of them that can be used to trap things in the future. There was a third group, and that was led by Lulu Kwan, and we read about Lulu earlier, a biochemist out of the California Institute of Technology out of Pasadena. And Lulu came up with a new way to create flat DNA origami-based images using a multi-stage assembly process. The researchers created origami-based pixels that appear in different shades when viewed with a device called an atomic force microscope. They assembled dozens of pictures into individual arrays, and then they tiled them together for 64 separate arrays to render an image of the Mona Lisa. Researchers have previously shown that they can decorate smaller DNA creations with everything from nanoscale metal particles to fluorescent chemical compounds, which might one day be useful for making novel electronics and photonic devices and then putting them inside of you. So then on Nano.gov, I also ran across the President's 2018 budget for nanotechnology innovation. This is submitted to Congress May 23rd, 2017, and it serves as the annual report of the National Nanotechnology Initiative for the United States, provided under the provisions of the 21st Century Nanotechnology Research and Development Act. The report also addresses the requirement of the Department of Defense reporting on its nanotechnology investments. Well, good thing. The President's 2018 budget, remember, DARPA was very deeply involved in nanotechnology. The President's 2018 budget provides for $1.2 billion for the National Nanotechnology Initiative, an investment in support of innovation promoting America's interests, including competitiveness, economic growth, and national security. The National Nanotechnology Investment proposed for 2018 reflects an emphasis on broad fundamental research in nanoscale to provide a continuing pipeline of new discoveries that will enable future transformative commercial products and services. The budget supports nanoscale science, engineering, and technology R&D at 12 different agencies. And you can see the agencies above, and we talked about those earlier: National Science Foundation, National Institute of Health, and all those other ones. Each year, the National Nanotechnology Initiative supplement to the President's budget features a cover image illustrating recent developments in nanotechnology stemming from activities that have the potential to make major contributions